Math and Engineering Help Desk. Today we're just going to talk about some exponent rules and some scientific notation rules and procedures. This is a summary of basically the past 3 lessons that we have had on exponents and scientific notation, and we're going to expand on it a little bit further, but let's go over just sort of the meat and potatoes of what we're talking about. Wanted to show you and remind you that when we have exponents, we have a base and we have an exponent. So this whole expression is called a power expression. That means that there's a base that is being multiplied a certain amount of times, and that number of times is based on the exponent. So if we had, for example, 10 to the third, that would really mean 10 times 10 times 10, okay? Which, as you know, would work out to be 1,000, okay? And if we had 10 to the second, how many times would we multiply 10? We would multiply 2 times, so that would be equal to 100. And if I did it just 10 to the first, that would just be 10 times itself one time, right? And that would equal 10. So you'll notice that if I kind of look at these first 3, that I've got 1,000, then 100, then 10. So there's kind of a pattern going on here, right? The exponent's going down by 1, down by 1. What should the next number be? So the next number is actually just 1, okay? And the reason for that is because 10 to the 0th means if I multiplied 10 by itself 0 times, and that's one way to look at it, but in reality, there's a couple of rules that will illustrate that you'll see in this next slide why it's equal to 1. And we can kind of just follow the pattern. The other way we can look at it here is if I have 10 to the third, that's going to be 3 zeros after the 1, 2 zeros after the 1, 1 0 after the 1, and 0 zeros after the 1. And then you might say, okay, well, how about 10 to the negative first? What does that mean, right? Well, when we have a negative power, and we're going to see this in a formal rule in just a second, we have a negative power. This is actually a reciprocal. So that means 10 to the negative 1 really means 1, right? But then divided by, let me draw my little fraction line there, and that really means 1 divided by 10 to the first, okay? And that really means, if 10 to the first, what's 10 to the first again? It's 10. So really, this 10 to the negative 1 is 1 over, equals 1 over 10, okay? So another way to look at that is if I look at the decimal equivalent of that, that's equal to 0 and 1/10, 0 and 1/10, okay? So we can also look at it as, well, we have negative 1 as an exponent here. We can think of it as there's how many zeros are before the 1. Right, so in this case, I'm going to put a decimal point in front to make sure of that. So it would be 0 and 1/10. And if I follow that pattern with this one, this would actually be 0 and 1/10. Okay, 100th, excuse me. So, and 10 to the negative 2 is 1 over 10 to the second. Right, so that's 1 over 100. So that fractional equivalent is 1 over 100. So if I keep going into the negative exponents, I'm going to get smaller and smaller in my denominator, which means my fraction overall is going to be small. It might be bigger in my denominator, but the whole fraction is going to be smaller. So we have this sort of understanding of positive and negative exponents just from this illustration of our powers of 10. Powers of 10 are very frequent. It's a base of the decimal system. It's also the base of the metric system. So it's something to start getting comfortable with, our powers of 10. Now let's look over our regular rules that we have so far with simplification. When we simplify expressions that have factors that are of the same base, we are instructed that we have to write them as one base. So if I had 3 to the third times 3 to the fourth, what does that really mean? Well, 3 to the third, as we learned before, is 3 times 3 times 3, right? And then I'm going to be multiplying that by, well, 3 to the fourth is 3 times 3 times 3 times 3, right? So how many 3's is that I see on this expression? Well, if I count them up, I see that I'm going to have 3 to the 7th as my resulting expression. 3 to the 7th is a larger number, obviously. You don't need to write that in standard notation. You can just write it as 3 to the 7th. The nice thing about exponents is it makes it easier to write very large numbers. Okay, 3 to the 7th is a pretty large number. But notice what we did here, okay? If I highlight the exponents in my original, I've got 3 and 4. What do you notice about 3 and 4? That equals 7. Right? So that means that when we have the same base and we're multiplying across, that just means that all we need to do is add the exponents, right? So if I had x to the n times x to the m, that's equal to x to the n plus m, right? We would just add whatever the exponents are of n and m. Okay, so if it was 3 and 4, it would be 7. The opposite is true if I have a quotient of two power expressions. So if I have 5 to the 5th over 5 to the 2nd, again, we can kind of think of that as how many 5s are up top and how many 5s are on the bottom. And when we divide, our goal is to try to cancel out stuff, right? So when we divide, we have 5 times 5 times 5 times 5 times 5, right? 5 5s. And then I'm going to be dividing that by how many 5s? Well, on the bottom, I've got 2 5s, right? So when I think about how I would solve this, I would just be trying to cancel out pairs of 5s. And the reason I do that is because what's 5 divided by 5? It equals 1. So I would be crossing off this 5, and I'd be crossing off this 5, right? So I'd be left with 3 5s altogether. So that means that the result of this is 5 to the 3rd. And I could say 5 to the 3rd over 1, but of course, I don't need to write a 1 that has that's a 1 in the denominator, right? So I know that that equals 5 to the 3rd. Okay, now again, notice the same thing, right? If I had 5 up top and I have 2 on the bottom, that's 3. So what did I do to get that? I did 5 minus 2, and that equals 3. So if I ever have a quotient of the same base with different exponents, all I really need to do is subtract those exponents. Okay, so that's the main understanding on here. Okay, so if I had the same exponent and same base, excuse me, and I'm multiplying, I would add their exponents. If I have the same base and I'm dividing their exponents, I would just subtract. Sorry, if I was dividing those numbers, I would subtract their exponents. And I just want to remind you of the vocabulary here. X is a base. Any number that is raised to an exponent is considered a base, and the bases have to be the same for you to do this. So one little counterexample: if I had 2 to the 4th and I was multiplying that by 3 to the 3rd, I would not be able to say that it's like, say, 6 to the 7th. Okay, that is not true. Okay, I can't do that because the bases are not the same. And if I were to test this out practically, that would mean that, 2 to the 4th times 3 to the 3rd, that should work out to be whatever 6 to the 7th is. That is clearly not the case. You can use that in a calculator and see that that's clearly not the case. Your only solution here, if you really want to know what this equals, it would be to expand these. 2 to the 4th is 16, 3 to the 3rd is 27. 16 times 27, that would be approximately 400 something, right? 450 something. So that would clearly not be 6 to the 7th. Anyway, let's move on. What if I have power of a power? That means I have a power expression that is raised to a second exponent, right? So that's power of a power. So there's a power here and there's a power here. What do you do? Okay, well, if we expand this out and understand its meaning, we can see clearly what to do. 3 to the 3rd is 3 times 3 times 3, right? So that's really what's inside these parentheses. That 3 on the outside means that I have 3 of these expressions. So that means I've got 3 times 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 3, right? So that's really what this means. If I expand this whole thing out, 3 of these. So how many 3's do you see altogether? If you count them up, you should see that you have 9 of them. So 3 to the 9th would be the answer here. Well, what does that mean? How could I maybe take a shortcut of do this, right? So if I had 3 and 3, how do I get 9 out of 3 and 3? Well, if your answer was, hey, you just multiply those two, that is absolutely correct. If I take the power of a power here and I multiply those exponents, that would give me the resulting exponent for this base. So the rule here is that if I have a power of a power, I just need to take the exponent inside times the exponent on the outside, and it would just be that, x to the mn. And remember, there's no multiplication symbol between here. If there's no symbol between them, it is multiplication. Now, just a brief review of the negative exponent rule before we see some scientific notation examples. Reminder that if I have 4 to the negative 2nd, what's the reciprocal of that, right? So when I say a reciprocal, I mean the flipped version of that. So in this case, it'd be 1 over what? Okay, well, if 4 to the negative 2nd is our starting number, if I flip that one, I would make it 4 to the 2nd, right? Sorry, my fraction bar is not straight, but that's okay. It'd be 1 over 4 to the 2nd. And if I really wanted to write that as a regular number, that's 1 over 16, okay? But notice that sort of what we're doing here is if I have a negative exponent, I like to call it a flip and switch, okay? And what I mean by that is to, flip the fraction and switch the sign, okay? flip the fraction and switch the sign. Let me just get that on one line. There we go. Okay, flip and switch. So we take this number, we flip it, we put the 1, there was a 1 on the bottom here, now we pick it on the top, and that 4 to the negative second is 4 to the second. And you might say, hey, wait a minute, what do you mean a 1 on the bottom? I don't see a 1 on the bottom. Remember that when the denominator is 1, you don't have to write it. So if you have a regular number, technically it has a denominator of 1. Okay, but you don't have to write it. However, when I say flip and switch, I want this number on the bottom and this number on the top, right? So that would go up here, and then this would go down here. And then the switch part refers to the sign of the exponent. So instead of it being -2, it now becomes +2. So the rule is when I have a base that is raised to a negative exponent, that solution or that simplifying is going to be 1 over the positive version of that same exponent, same expression. Okay, so x to the negative n, instead on the bottom I would use 1 over x to the n. Okay, and that would be the negative exponent rule. Now, how does this apply to scientific notation? Well, scientific notation, remember, this is our method of expressing very large or very small numbers. You really could express any number in scientific notation, but there's kind of 2 little caveats to that. Number 1, this a, this base number in scientific notation, the lowest this number can be is 1. The greatest that it can be is 9.9, or really 9.9 and repeating, right? So in other words, this number, this a, needs to be between 1 and 10, but not 10. Okay, so it could be 9.9999999, right? But it can't be 10. So that first number here is required to be between those 2 numbers. And if it's not, we'd have to simplify it. We'll talk about that in one of the examples. The b just has to be an integer, okay? So b is an integer. So if it's not an integer, then it's not considered scientific notation, okay? The exponent needs to be an integer. That doesn't mean that the whole number needs to be an integer. That just means that the exponent of 10 needs to be an integer. And all scientific notation always uses powers of 10. Okay, now let's talk about multiplying in scientific notation. It's actually the easiest of the 4 operations that you would need to do in order to operate in scientific notation. So if I have 3 times 10 to the 3rd and I'm multiplying by 2.5 times 10 to the 4th, here's what we really need to do. If I'm going to multiply this out, let me just change the text color a little bit. Let's go with purple. What that really means is I'm going to be taking the 2 a values, the numbers in front, and I'm going to multiply those. So 3 times 2 to the 2.5 in this case. And then I'm going to be second taking the powers of 10 and multiplying those. So 10 to the 3rd times 10 to the 4th. Oops, I went too soon on the exponent there. 10 to the, still too soon. 10, there we go, to the 4th. Okay, Mr. C wrestles with formatting issues. Okay, so that means when I multiply in scientific notation, I'm just basically matching up the a's and matching up the powers of 10 and just multiplying those 2 numbers, right? So 3 times 2.5, that's going to be 7.5. And 10 to the 3rd times 10 to the 4th is 10 to the 7th. And that's it. Okay, so what we're doing is we're, again, multiplying, we're matching the a values and the b values. Okay, that's all we're doing. When we multiply in scientific notation, that's all there is to it. So if I look at this next number, let's see if I can do this a little faster, right? So if I know of 1.4 times 4, well, 1.4 times 4 is 6.4. You can always use a calculator if you need to, right? And 10 to the 2nd times 10 to the 3rd, if I add 2 and 3, I get 5. Now, here's a special case, right? So if I have, let's say this number here, 6 times 10 to the 5th times 2 times 10 to the 4th. 6 times 2 is 12. And then, oops, I'll put the equal sign. 12. And then 10 to the 5th times 10 to the 4th is 10 to the 9th. Now, this is a special case because remember the rule I said earlier, which is that that b value cannot be between, has to be between 1 and 10. Well, 12 is greater than that, right? So what do we need to do? We need to make this number be lower, right? So 12 needs to become 1.2. Now you might say to yourself, well, how the heck did I do that? Why am I doing that? Whenever you have a number like this, the decimal point can be used to make it between 1 and 10. Now, if I make 12 and I make it 1.2, I have really divided this number by 10 by moving the decimal point over, right? So if I'm dividing it by 10, I'm going to make up for it by adding a power of 10 to my base, right? To my b value. So think of it as I'm compensating by making this number smaller by making this number larger. In the event you have a number that's too small, you could increase this size and make this number smaller. So you kind of just think of it as a balancing act, right? So that's a little harder to process in some cases. What you could always do is use your calculator's feature to convert a number to scientific notation if you're not sure if you're doing it properly. That will take time. And then the last example here is I just want to show you with this negative exponents, the rule is still the same even though they're negative exponents, right? So if I have 6 and 1.5, that's 9, right? 6 times 1.5 is 9. And then if I use the same principle of adding the exponents, negative 5 plus negative 1 is negative 6, okay? So that means, oops, superscript, there we go. That means that this answer here is 9 times 10 to the negative 6th, okay? Now, again, that makes sense based on the rules. You're just doing the a values multiplied together and the exponents added together, right? And you might say to yourself, well, why is this exponent like smaller than either of these? You may recall that with negative exponents, these numbers are smaller, right? These are less than 1. This is even more less than 1. That makes that if you're multiplying a small number by a small number, you're going to get a smaller number, right? Especially if the numbers are all less than 1. So it makes sense. All right, now let's just do a couple quick examples on division and then we'll end this video, okay? Dividing is no different, right? You're just going to do the same thing as you multiply, except you're going to divide the a values and you're going to subtract the exponents. So if I have 5 times 2 to the fifth, so I have 5 divided by 2 to the 5th, that's going to be 2, right? And then if I have 10 to the 4th divided by 10 to the 3rd, that's 10 to the 1st, okay? And you may know this number better as 20 in standard notation, 2 times 10, right? Okay, and then what about here? Now this one's a little different, right? Because here I have a positive exponent on the top and a negative exponent on the bottom. So that means I have a number that's greater than 1 on the top and I'm dividing by a number that's less than 1 on the bottom. Now, if you may recall that if I divide by a smaller number, a number less than 1, my quotient is actually going to be larger than the factor I'm dividing, or the dividend. So that's, knowing that, this will make sense of why this answer works out to be what it does. What's 4 divided by 4? It's going to be 1. And then 10 to the 2nd divided by 10 to the negative 3rd, that's 2 minus negative 3. That means that this exponent is actually 5. So if I also think of this in standard notation, this is 400 divided by 4 10,000ths. And that makes sense now that I have 100,000 as my answer, okay? Now, dividing in scientific notation, very similar to multiplying in scientific notation. We're not going to cover addition and subtraction today. We'll talk about that in a future video, but I just want to give this up to you right here so you can watch this and check this out and then work on the examples in your slides, okay? I hope you have a wonderful day. Don't forget to be awesome.